Hello. These are the solutions to the remaining final exam review problems. So the first question, which atom has the most neutrons? An atom with an atomic number of 28 and a mass number of 59. Let's remember that the mass number is the number that would be written above the symbol. The atomic number will be written here. The atomic number is the number of protons in the nucleus of the atom. It's what defines the atom. The positive charge in the atom defines the atom. The mass number is the majority of the mass because the protons and neutrons carry most of the mass of the atom. It's the sum of the protons and the number of neutrons. The number of electrons are not included in the mass number because they are very light. So they are about 1/2000th the mass of a proton or neutron. So 59 is the sum of the protons and neutrons. So if I subtract 28 from 59, 59 minus 28 is 31. So I have 31 neutrons for A. Manganese is element number 18, element number 25. So this would have 30 neutrons. Iron is element number 26. So it would also have 30 neutrons. Chromium is element number 54. It's not 54, element number 24. So we're going to have 52 minus 24 for 28 electrons. Okay, so the most here is 31. So 31 has the most neutrons from A to D. E doesn't make any sense. So some elements like iodine exist naturally as just a single isotope, which is found in nature as iodine-127. What is the atomic weight of this isotope? So it's not going to be likely exactly 127.0000. The only isotope that's exactly a bunch of zeros is carbon-12, because this is defined to be 12 exact AMU. So the other ones aren't exact. The way you would know iodine's atomic weight is you would go to the periodic table and look at the average atomic weight listed. So the periodic table for a given element lists the average atomic weight. And if an isotope only exists as one, then it's the isotopic mass of its only isotope, in this case, iodine-127. So a few nomenclature questions. So let's name the following compounds. So we got K2CO3, this is carbonate, and that's potassium ion, so that's potassium carbonate. ClO3 minus is chlorate, so this would be sodium chlorite. So the things to remember would be like sulfate is a 2 minus with 4. Chlorate, like we see here, is 3 with a minus. Bromate is 3 with a minus, BrO3 minus. Nitrate is 3 with a minus. Phosphate is 4 with a 3 minus. So these are just some common ions that I think we should know. Of course, carbonate as well. And then if you lose an O, keep the charge the same, then this would be ite, bromite, nitrite, phosphite, carbonite. If you lose a second O, which is only common in the case of like the chlorine and bromine and iodine molecules, but if you have ClO minus, this would be hypochlorite. And then we'd have Cl, if you add an O, ClO4 minus, pick up an extra O, we go per, so perchlorate. So a couple other examples here of going to formulas from the name. Iron 3 plus. Iron 3 is iron 3 plus. Oxide is a 2 minus. This is a simple oxide ion. So we have Fe2O3. So the formula wouldn't contain the charges in it, so just Fe2O3. Magnesium sulfate. Magnesium is a 2 plus. Sulfate's a 2 minus. So we'd have MgSO4. If you had like magnesium phosphate, you just have a 3 and a 2, put some parentheses here, so that would be magnesium phosphate. Which set of quantum numbers would describe the most easily removed electron from a copper atom? So copper Well, has one of two configurations you might be considering here. 4s2, 3d9. If you knew it had an anomaly, you might be thinking it's a 4s1, 3d10. This is its actual configuration, but this is the one you would probably expect. But to answer this question, it doesn't really make any difference because in either one, this is the electron you would expect to be lost first. So copper plus would have either a 4s1, 3d9 configuration, or probably its actual configuration would be 3d10. But still, the electron you would lose, describing the electron that you're going to lose here, would have an n equals 4, L equals 0, because that's what S means. The only M sub L is 0. And then the M sub S could be plus or minus a half. And it wouldn't make any difference if it were plus a half or minus a half. So it looks like this would be the proper set of quantum numbers. So again, this one could be plus a half or minus a half, but wrong N value here, wrong L values here, wrong N. So that's what makes those ones incorrect. So selenium, we're told here, the most common oxyanion, like carbonate, this is an oxyanion. Sulfate's oxyanion is SO4 2-, and they're saying selenium has the same number of O atoms and charge as sulfur. So the most common oxyanion of selenium would be this one, and the key would be that this is selenate. So if we're asked for the formula, we would expect for francium selenite, well, selenite would have a 3, and we're going to put francium out in front, which is an alkali, we're told. And so it's a plus, and so we're going to need 2 of these. So our formula should be Fr2 SeO3. Silicon carbide is produced by heating SiO2 and carbon to high temperatures. How many grams of silicon carbide, one of the products here, can be produced by reacting 2 grams of SiO2 and 2 grams of carbon? Well, what I'm going to do here, the way I would go about solving this problem, would be to work out the grams of product I can make from either one of the reactants fully reacting. Okay, and so what we're assuming here, like when we do the first step, for SiO2, the 2 grams to fully convert to silicon carbide, I'm going to need the proper amount of carbon to react with it to be present. And I don't know if I'm going to have the right amount, but I'll see by running through the calculation with carbon how much product I can get with reacting all the carbon, how much product can I get if I react all the SiO2, and we're going to see which one makes less. And so silicon 2809 plus 32 so that's 60.1. For every 1 mole, oh, I wrote silicon carbide, but I should have wrote silicon O2. So this is the molar mass of SiO2. I wrote the wrong value. I wrote the right number, but the wrong thing. So the molar mass of SiO2 is really 60.1 grams per mole of SiO2. So 1 mole of SiO2 is required when it reacts to produce 1 mole of silicon carbide. So if all the SiO2 converts to silicon carbide, so this is going away, this is forming, then 1 mole of silicon carbide would have a molar mass of 28.09 plus 12.01, so that's 40.1 grams. So 2 divided by 60.1 times 40.1. So that's 1.33 grams of product. Now, how much would we get if we react all the carbon? And so what this means here, to get this much silicon carbide would mean we react all the SiO2, it's down to 0, with the proper amount of carbon to produce this much silicon carbide. Well, let's see how much silicon carbide we get if we produce all the carbon. So 12.01 grams per mole of carbon. For every 3 moles of carbon that react, and are lost, we produce 1 mole of silicon carbide. And then for every 1 mole of silicon carbide, it's, of course, the same mass, 40.1 grams. So 2 divided by 12.01 divided by 3 times 40.1 is 2.23 grams. Okay, so in order to get 2.23 grams of silicon carbide, I'm going to need more SiO2 to be present, because if I react all the SiO2, I only get the 1.3 grams of silicon carbide. To get the 2.23 grams, I need more SiO2 to have been present. So I will run out of SiO2. The reaction is going to stop when I hit 1.33 grams of silicon carbide. So the key with this approach here is we're looking for the one that makes less. Once we reach that lesser point, the reaction is going to turn off. That's the most we can make. So 1.33 grams is our the amount of silicon carbide we can produce by this reaction. So given some thermodynamic equations, we're asked to calculate the delta H of an unknown reaction or this other reaction. So what I want to do here is use Hess's law. So I want to rearrange these reactions. And so I'm just kind of inspecting here, seeing BRF here. So I need bromine fluoride to be on the reactant side. So I'm going to flip this reaction. I also need to cut the coefficients in half. So I'm going to have BRF goes to a half BR2 plus a half F2. The delta H of this reaction is the negative of 188, so it's plus 188. And then I need to multiply the coefficients by a half because I cut the coefficients in half. So what I did to this reaction is I flipped it and I cut the coefficients in half. I cut the coefficients in half because there's 1 BRF here. I need there to be 1 BRF here on the reactant side. And then I have the right number of BRF3s on the product side, or I have BRF3 on the product side, which is good, just the wrong amount. So I need to cut this coefficient here by half. So if I can write this in here, I'd have a half BR2 liquid plus 3 halves F2 goes to BRF3. The delta H would be minus 768 kJs times a half. So what I'm doing is I'm adding these reactions up. I'm adding up reaction 1 and now my rearranged reaction 2. If I add those up, notice that my BR2 cancels, a half BR2 on both sides, and then I have a half canceling with 3 halves, so down to 1. So that's how I get BRF plus F2 goes to BRF3. So this is just a puzzle. I just need to see how I adjust my delta H's. So the first one was plus 188 times a half. And then the second one, I'm adding 768 negative times a half. And so this works out to be negative 290. If you need to, write these out bigger, so you can see what's going on more clearly if the small text is getting in the way. And then we have BR2, a half, plus 3 halves F2 going to BRF3. So 768 negative times a half is minus 384. And so again, the idea is we're adding these reactions up. That's why these cancel here. And a half and 3 halves cancels down to 1. So we have BRF plus F2 goes to BRF3. Delta H is these two values added together, minus 290 kJs. So how much energy is released when when a tenth of a mole of diborane reacts with oxygen? And we're given some thermodynamic information. So what I want to do is write out the reaction that's taking place. So I have B2H6 reacting with oxygen to produce B2O3, and then plus steam. Steam is water vapor. If I want to balance this reaction, let me balance the hydrogens first. So I have 6 hydrogens on both sides. Now I have 3 O's plus 3 O's. I have 6 oxygens, so I need 3 O2s. So I have 6 O atoms on both sides. I have 2 borons. And so the delta H of this reaction is going to be the sum of the products minus the reactants, standard enthalpy of formation values. So this is how I'm going to take minus 1272 times 1 mole. There's 1 mole of this in the reaction. And then I'm going to add 3 times that of water gas. So this is the sum of the delta HFs of the products, the final state, minus the sum of the reactants. And so 1 mole times B2H6, which is 35. So the mole cancels here. So I have minus 1272 plus 3 times 241 negative, and then minus 35 gives me minus 2030 kJs. Now this energy here is per 1 mole of B2H6 because there's 1 mole in the balanced reaction. And so all I need to do now is multiply by 0.100 moles of B2H6. So I got to get this coefficient from the reaction, which is just 1, but that's easy enough. And so I need to multiply negative 2030 by 0.1. And so I get minus 203. And then that's kJs. The Q reaction is minus 203. This reaction is exothermic. So heat is released. So 203 kilojoules is released. Released is here, this implies that the Q reaction is negative. This implies an exothermic reaction. Which species has the same shape as ammonia? So ammonia has the shape of trigonal pyramidal. And so which of these has a lone pair on a central atom? It's not any of these because these are all trigonal planar. Why are these trigonal planar? Well, like SO3 has 3 oxygens. And then if we count the electrons, we have 24 electrons. So we have no leftover electrons for the central atom. We might make a double bond. We might make 2 more double bonds, but the key is no lone pair on sulfur, trigonal planar molecular geometry from having 1, 2, 3 domains. If we look at nitrate as well, has 24 electrons. So nitrate, we have essential nitrogen, 5, 3 times 6 plus 1, that's 24 electrons as well. So again, I'm going to have 3 oxygens connected to nitrogen. I'm going to make 1 double bond here. Again, no leftover electrons, though, for the central atom. The same thing with carbonate. Carbonate also has 24 electrons. This is just a carbon here instead. And so for carbonate, also no lone pairs on the central atom. SO3 2 minus 6 plus 3 times 6 plus 2, now I can have, with 26 electrons left over for the central atom. So I have sulfur, oxygen surrounding it. That's 24 electrons, the 2 left over onto sulfur. And so SO3 2 minus is the one that has the lone pair for a domain and then 3 bonding domains. So it also is trigonal pyramidal. let's see here. So we have A2 plus B2 goes to 2AB2, delta H given. The reaction takes place at constant temperature in a container that's a good conductor of heat and is filled with a movable piston. So we just have the reaction taking place here. And so which observations seem reasonable? So what's going on here, we're starting from 3 moles of gas, and we're forming 2 moles, we're starting from 1 mole of gas, this is a liquid, and then we're producing 2 moles of a gas. So we're increasing the moles of gas, so that's going to lead our piston to expand to keep a constant pressure. And so our volume should increase because we're creating more moles of gas during the reaction that's taking place. And so the piston should move outward, and then the reaction is endothermic. So the container here, let's imagine it's in a water bath. The temperature of this water bath is going to change because the heat is flowing inward. And so heat is flowing into the reaction because it's endothermic. It's absorbing heat from the water. So the temperature of this water should drop. So the temperature of the water surrounding the reaction should decrease because the reaction is endothermic. So the Q reaction is positive, negative Q of the surroundings. So the surroundings heat is dropping. The water is the surroundings. And so the temperature of the surroundings should feel like they are decreasing in temperature. So the piston moves outward and the container feels cold. Last couple of questions. So which resonance structure contributes most to the overall bonding in nitrous oxide N2O? So we have a central nitrogen, oxygen outside. So if we're building the Lewis structure following our basic ideas here, so we'd have 5 times 2 for nitrogen plus 6, 16 electrons. So this is the proper count distributed, none left over for the central atom. So the question becomes, do I make this double bond here? And sure, because we had a high formal charge. Right now, my formal charge on nitrogen is +2. It was +3, so that's better. I can reduce the formal charge by making another double bond. And so I make the double bond here. The formal charge drops to +1. So reducing formal charges is good. This nitrogen, the outer one, has 5 electrons surrounding it. So its formal charge is 0. And then this formal charge on oxygen is minus. And then this is as far as we can go. Like I can't do this here because this would allow the octet to expand of nitrogen, which it can't do. So I can't do this because this leads to 10 electrons around the central N, and that's too many electrons. So that violates the octet rule. Second row atoms cannot expand their octets, so and it's not a choice either. So the best structure is going to be this one here. Right formal charges are shown, plus and minus on O. Now, why are some of the other structures bad? Well, that lone pair is not on N, so that's bad. This structure here is just kind of nonsense. I don't know what to make of that one. So I just would say we never really considered having those types of cyclic bonds, so I wouldn't go with that answer. And then answer D is bad because if we go back to having this structure here, where we were trying to figure out if we should make a second bond, we have the 2+ formal charge, we have the minus formal charge here. This one comes from making the double bond here, which now gives us a 0 formal charge on O and a minus formal charge on N. So if we're choosing between, let's call this structure A and call this structure B, B is better because we're keeping the negative charge on the more or less negative atom. So when all else is equal, when we're satisfying the octet rule for all atoms the same way, but the only difference is do we put the negative charge on the O or the N, we put the negative charge on the O. Now there were some Lewis structures where we didn't do this, but it was for a different reason. If you go to like ClO minus, this structure here, if you remember, we were choosing, well, I think it might be ClO without the minus charge. That is more interesting. But let's look at ClO minus. First, I have 7 plus 6 plus 1, 14 electrons. So I kind of have no choice but this Lewis structure here. Now, if I want to go to ClO, if I want to kick an electron off, do I kick one off of the Cl or do I kick one off of the O? So for ClO, do we go with ClO, this structure here, or do I go with the ClO structure where I remove the electron from O? This is actually a little bit of a tricky question because this one here has a minus but a plus, and then this one here actually has a 0 and a 0. So why is this 0, 0? Well, chlorine should have 7 electrons surrounding it, and the chlorine here has 1, 2, 3, 4, 5, 6, 7. So I have a 7 minus 7 for 0. Oxygen should have 6 surrounding it, and I have 1, 2, 3, 4, 5, 6 surrounding it for 0. And so I'm violating the octet rule here on one of the atoms. So, and then also the formal charges are different between the two structures. And so, generally we want to minimize the formal charges when it's possible, but then also we don't want to maximize formal charges either. So we have different constraints of different molecules for different reasons, which does make this maybe confusing at times, but I think it just becomes a matter of trying to think of, well, what are the reasonable Lewis structures you can sketch? What makes them similar? What makes them different? And then try to evaluate which ones make more sense. So what we come back to the N2O1, what we're evaluating between is, do we, put the more negative charge on the O or the N? There's no structure we can write that makes both of those go to 0. And so there's no way we're getting the 0 and 0 on both those atoms, on the central N and the O or the N. So that's why we want to keep the negative charge on the O and go with answer A. Okay, so with that, let's look at 53 real quick. So for 53, a little bit of a tricky question, but I might do a couple related examples. So the molecule allene is H2C. So I have 2 hydrogens connected to a carbon. And then I have the 2 carbons connected. So I go H2C, and then another C, and then another C, and then another H2. And then in order to get our octet satisfied for the carbon, it also likes to form 4 bonds, I do 2 double bonds. I doubt you'd have to necessarily interpret a Lewis structure like this. We might just show you the Lewis structure so you don't have to necessarily come up with the Lewis structure and then answer a question. But so if you're looking at this Lewis structure and have it sketched out in front of you, I think this question is pretty easy, right? Because we're saying this is a sigma, this is a sigma. This and all 3 of these carbons are sp2, meaning I have these sp2 orbitals, and I have an sp2 orbital here giving us a sigma, and then I'd have the p orbital left over making a pi bond. So my C double bond C, this is a sigma plus a pi, and then the other carbon-carbon double bond is a sigma plus a pi. And then the hydrogens are sigma bonds. And then the other carbon to hydrogen are sigma bonds as well. So I have 1, 2, 3, 4, 5, 6 sigmas. And then I have 2 pi bonds. So 6 sigma, 2 pi. Let's do another example. Let's look at one again where you have the Lewis structure shown. And let's even, identify hybridization. So our hybridizations of the atoms go along with like the trigonal planar for this carbon. Trigonal planar is sp2. And so I'm going to have this double bond be a sigma and a pi. The sigma is the sp2 overlap. Oxygen should have some lone pairs on it. So you can think of oxygen as being sp2 as well. So I have sp2 orbitals here, hybrid orbital here, making the sigma, leftover p orbitals making the pi. And then these 2 atoms here we might say are sp hybridized because they're linear. Linear because the carbon and the nitrogen have 2 domains each. And so sp overlap would be the sigma, and I get 2 pi bonds. So I'm going to have a total of 1, 2, 3, 4 sigmas, and then a total of 1, 2, 3 pi. So the key is just being able to describe the bonding. One last example might be to say, well, for something like formaldehyde, can we describe what's going on here in terms of bonding? Like this bond here is made about by 1s, and then the sp2 overlap of carbon. So this is the overlap that makes the sigma bond between H and C. That's our CH sigma. The other CH bond exactly the same. And then we have our sp2 atom. We can have the sp2 overlap. So we have sp2 overlap between the C and the O. This is our sigma here. And then the pi would be the 2p overlap. So just kind of breaking down the bonding in something like formaldehyde. So we're going to get 1, 2, 3 sigmas and plus a pi. All right, so that will conclude our final exam review packet.